We've all seen those incredible videos of super agile robots, right? But what happens when the hidden math behind all that graceful motion suddenly breaks? Well, today we're going to explore exactly why robots get stuck and how a really cool breakthrough in AI simulation is helping them learn to get unstuck way faster than ever before. You know what I'm talking about. You see this complex robotic arm, it's moving perfectly, and then it just stops, completely frozen in some weird position. And it's not a bug in the code, at least not in the way you'd think. It's actually a problem that's baked right into the physics of how it moves. So yeah, let's get to the bottom of this robotic paralysis. What is really going on when a machine that's designed for super precise motion suddenly can't move at all? Okay, the official term for this is a kinematic singularity. Now, kinematic is all about motion, and a singularity, well, that's a point where things just go haywire. The robot has basically maneuvered itself into a mathematical dead end, a spot where it physically can't move the way it's being told to. And this isn't just one single type of problem. It turns out a robot can paint itself into a corner in two main ways. So first up, we've got what's called a boundary singularity. This one's pretty intuitive. Just picture your own arm stretched all the way out. You can't reach any further, right? That's it. The robot's trying to get to a point that's just outside its maximum reach. Then you have something a bit more sneaky, an internal singularity. This happens when two or more of its joints line up just right, in a way that kind of cancel each other out. The robot gets trapped by its own internal geometry. And here's where it gets really wild. To make even a tiny movement in one of those stuck directions, the math tells the robot's joints they would need to spin at an infinite speed. Obviously, that's impossible. So the controller just freezes everything to stop the motors from burning themselves out. Okay, so if these positions are so bad, how have engineers been dealing with them for all these years? Well, they developed a kind of mathematical crystal ball to see these problems coming before they even happen. You see, for robots doing the same thing over and over, like in a car factory, engineers can pre-plan every single movement. They use this special tool to map out the entire path and just make sure it never even gets close to one of these problem spots. And that special tool, it's called the Jacobian matrix. The easiest way to think of it is as a translator. You tell it how fast each joint is turning, and it translates that into the final speed and direction of the robot's hand. It's the key link between the parts we control and the part that actually does the work. So here's the rule that engineers live by. They calculate a single number from this matrix. It's called a determinant, and it acts like a warning light. If that number ever hits zero, bam, mathematical red flag. It's basically the same as trying to divide by zero in the robot's motion equations. The math breaks, and that signals a singularity. Let's try to make this a little more visual, though. We can actually graph this zone of possibility to see just how much freedom of movement the robot has at any given moment. It's called the manipulability ellipsoid. When the robot is in a good, flexible position, this bubble is big and round, meaning it can move its hand easily in any direction it wants. But as it gets closer to a singularity, that bubble gets squashed. It might flatten into a line, meaning it can only move back and forth. Or it could collapse all the way down to a single point, meaning it's totally and completely stuck. So that's the classic problem and the classic solution. But everything changes when we stop pre-programming robots and start letting them learn all on their own. And this is where the real challenge begins. On the left, that's our old factory robot. Its path is perfectly planned out, it will never hit a singularity. But on the right, that's a modern AI-driven robot. It has to learn through trial and error, by exploring its world. It's going to stumble into these singularities. In fact, it has to. That's part of learning. And here's the big, new problem. An AI learns from its mistakes, right? But if every single time it makes a mistake by hitting a singularity, the simulation just crashes because it's trying to divide by zero, how can it possibly learn anything? It never gets the feedback it needs to figure out how to do better next time. Now, the old way of getting around this in simulations is this brute force method called finite differences. And oh my gosh, it is so slow. You basically have to nudge every single joint, one by one, rerun the entire simulation, and measure the result just to figure out which direction is better. As the research paper puts it, for a complex robot, this method is quickly prohibitive, which is a very polite academic way of saying it's impossibly slow. You would literally be waiting for years for an AI to learn even a simple task. We needed a much better way. And this brings us to the breakthrough. Instead of simulations that just crash and burn, what if we could build simulations that actively teach the AI how to improve, even when it gets itself into one of these stuck positions?
The solution is a totally new kind of simulator that can instantly calculate something called a gradient. And a gradient is just a fancy word for the direction of steepest improvement. So instead of the AI just guessing randomly, the simulation can literally tell it, hey, to do better next time, you need to change your joints in this specific way.
This is called differentiable simulation. That key word, differentiable, basically just means that the simulation can always calculate that hint, that gradient. The math never breaks down. So the AI gets useful feedback from every single action, even when it gets near those really tricky singularity points. The magic that makes this possible allows the simulator to handle all the messy, real-world physics, things like friction and contact, without having to oversimplify them, so the simulation is both incredibly fast and realistic. So how much of a difference are we talking about here? Well, the numbers are just staggering. To calculate one of those learning hints for a simple robot, the old method took 1,100 microseconds. The new differentiable method? Just 14.7. Let's just put that number up on its own so it can really sink in. This isn't just a small improvement. It's over 70 times faster. This completely changes the game for training AI robots. Something that used to take a week might now take just a few hours. And that really brings us to the final thought here. This isn't just about preventing a robot arm from freezing up. This is about fundamentally speeding up how quickly an AI can learn to interact with the physical world. If learning from a mistake is suddenly 70 times faster, just imagine the kinds of complex, messy, real-world tasks they're going to master next.